Kubernetes has a number of purposes. One of them is to abstract away the details of the underlying cluster and its hardware, but volumes fail to do so. For a developer to create a volume, they need to know the details like who their storage provider is. For instance, you need to know that you're using, say, Amazon, and therefore you need to use an Amazon Web Services EBS volume. The Kubernetes development team noticed this situation. They decided that Kubernetes needed a mechanism which would abstract away the details of providing storage from the details of consuming storage. This way, developers can just request storage without knowing about the underlying storage technology. Then the underlying storage provider details can be left in the capable hands of a cluster administrator. This way of provisioning and consuming storage uses two new Kubernetes objects, persistent volumes and persistent volume claims. There are three key things which define what a persistent volume is. First, a PV is a storage resource. It's a resource just like a node is a resource. That means that A, it is something that can be consumed, and B, it exists outside of any namespace. Second, a PV is not provisioned by a developer, aka a user. It's either automatically created by Kubernetes for the developer, or it's provisioned by a cluster admin. Third, persistent volumes have a lifecycle which is independent of any one pod. There are also three things which define what a persistent volume claim is. First, a PVC is a request for durable storage by a user. A PVC is then bound to a PV. This is how PV resources are consumed. Second, pods use PVCs as volumes. This is why one of the valid volume types is persistent volume claim. Third, PVCs must exist in the same namespace as the pod using them, as opposed to PVs, which you'll recall, exist outside of all namespaces. Before we get into some examples, I think it'll be really helpful for you to understand the life cycle of persistent volumes and persistent volume claims. So let's start at the beginning with provisioning. The first thing that happens is that a cluster admin creates a persistent volume. This is called static provisioning because the admin manually creates the PV. There's also something called dynamic provisioning, which we'll get into later. The next thing that happens is that a cluster user creates a persistent volume claim. The claim specifies how much storage it needs and the rewrite access modes that it requires. Kubernetes then tries to match the claim to an existing persistent volume. Any PV which meets or exceeds the claim's requirements is a valid possible match. The cluster will always bind the claim to the closest matching PV. For instance, let's say that you have a claim which requires 1 GB of storage. And let's say that there are only 3 persistent volumes with 512 megabytes, 3 GB, and 4 GB respectively. Kubernetes will bind the claim to the 3 GB PV since it's the best valid match. So what happens if there are no persistent volumes which match a claim? The answer is that the claim will remain unbound until a valid persistent volume becomes available. This means that cluster administrators can create new persistent volumes on the fly to fulfill unsatisfied claims. One last thing, PVCs bind to PVs in a one-to-one manner. This means that the owner of a PVC has exclusive access to the PV which it's bound to. Nothing preempts the binding until the claim owner is done with the persistent volume. From a pod's perspective, a persistent volume claim is just another type of volume. That means that a pod can mount a PVC onto its file system just like it would mount an empty dir volume. Once a user is done using a persistent volume, he or she can delete the associated claim from the cluster. This gives Kubernetes the opportunity to reclaim the PV. How the reclamation process actually plays out depends on the PV's reclaim policy. There are 3 possible reclaim policy values. They are retain, recycle, and delete. The retain policy dictates that a persistent volume is not freed up for reuse after a claim has been deleted. A cluster admin must first delete the PV, then delete all the old user data from storage, and then delete the associated storage asset or create a new PV which reuses the storage asset. The recycle policy is in the process of being deprecated, so avoid using it. Finally, the delete policy instructs Kubernetes to delete the persistent volume along with the underlying storage asset, such as an AWS Elastic Block Store or a GCE persistent disk. This is a host path PV config file. You can tell by the fact that the kind is persistent volume and there's a host path field. Host path PVs should only be used for prototyping on a single node cluster. Although you won't use it in production, a host path PV still looks and acts like other PVs. Plus, it works on Minikube. Thus, we're going to go over this host path config file to learn about how PVs work in general. The storage field gives you the means to specify the amount of storage space required for this persistent volume. You may specify the storage capacity using SI suffixes or power of 2 suffixes. Just to make sure that we're on the same page, let's review that stuff. Here's the list of SI suffixes. Confusion commonly stems from the fact that these same SI suffixes are often used to mean the power of 2 equivalents. This is not technically correct, but it's a common occurrence outside of Kubernetes. If you want to specify memory using power of 2 suffixes, then here's what they look like. Thus, these 3 values are roughly equivalent. One last thing. Suffixes are case sensitive in Kubernetes. The access modes field is a string array specifying the allowed access modes for the persistent volume. The read-write-once access mode dictates that the volume can be mounted in read-write mode by at most one node. The read-write-mini access mode dictates that the volume can be read-write mounted by many nodes. Lastly, the read-only mini access mode dictates that the volume can be read-only mounted by many nodes. There are 2 things to keep in mind. First, a storage system may not support all types of access modes. Second, a persistent volume can only be mounted using one access mode, even if it supports multiple. Then there's the host path field. You can use this field to mount a file or directory from the host node onto the container. This is something that's unique to host path persistent volumes because they store their data directly on the host file system. It's rare to need this capability, but it's a useful escape hatch all the same. Finally, here's the reclaim policy. Now that you've seen an example of a PV, let's create this one. The persistent volume's capacity is 5 megabytes, and the access mode is read-write-once. Notice that the claim field is blank, because this persistent volume is not yet bound to a PVC. Let's create a persistent volume claim which will bind to that persistent volume. We need to specify both the access mode and the amount of storage required by this claim. Don't worry about the storage class name field for now. We'll get into that in a minute. So let's create the claim and then use the get command to examine our work. The status field indicates that the claim was bound to a volume. We can examine the PVs and see that the one which we created has been bound to our PVC. Now I'm going to show you how to use a claim as a volume in a pod. Here we have the bat example pod. Both Batman and Robin mount the Batcave volume. But instead of using an empty dir volume like we did before, now we're going to use the example PVC. Nothing else has changed. Batman still creates a file called batmessage on the volume which Robin has access to. And Robin still sleeps to give us a chance to ls the shared directory. Now all we need to do is create the pod and then run the ls command on the shared directory in the Robin container. Hey, The bat message was created on the volume shared by the two containers. This proves that a PVC can be used as a volume on a pod.